Hello and welcome to my ITC571 project, Software-Defined Networking and its Effect on the Internet of Things. As I complete my Masters in Networking and Systems Administration, two phrases continue to pop up in my studies. One of them, the Internet of Things, interested me because of the sheer enormity of the concept and all its innovative ideas. The second phrase, Software-Defined Networking, or SDN, came up occasionally but I didn't understand what it was. This led me to investigate the issues associated with the Internet of Things and whether SDN could help to alleviate them. So to start my seminar, I'll run through the definition of the Internet of Things and the issues it faces. I'll move on to a brief description of traditional networking and its limits, finishing off with some talk about SDN and how it can help to continue to enhance the user experience of the Internet and its connected devices. The Internet of Things can be described as all devices which collect, transmit and exchange data over the Internet using any type of sensor such as a camera, temperature sensor, microphone or RFID tag. Cisco predicts that the Internet of Things will generate 600 zettabytes of data by 2020. That's up from 145 zettabytes in 2015. A zettabyte is 1 trillion gigabytes. It's huge, and all this data needs to move from one device to another in a timely manner. Keep in mind that only 10% of this data is saved, but that's still 60 zettabytes. The amount of devices connected to the Internet of Things will jump from 9 billion in 2015 to over 24 billion in 2020. Let's have a look at some examples. Spain has public bins installed with sensors to tell the garbage collection service when the bin is full. The Live Traffic app has cameras all over Australia streaming video of well-known congested roads for commuters to jump online and check before travelling. The Department of Primary Industries has put receiver tags on sharks to alert swimmers if one is in the area. These tags are picked up by a listening device connected to the Internet of Things. Smart houses can become energy efficient and improve the residents' experience by turning on and off devices to suit the requirements. A fridge can change its cooling to suit the contents and even create a shopping list which is sent to the supermarket to order home delivery. And a watch, or what they call a wearable these days, can send information to your smartphone about many things including your heartbeat, amount of steps walked, or where you ran, which in turn will be correlated with other information to assist in improving your health. This is only a few of the thousands of different devices connected to the Internet of Things and a fragment of what there will be in the future. There are three factors that need to be addressed which contribute to the success of the Internet of Things. The first is big data. This has come about by the need and want to gather huge amounts of information and share the information to make it useful. If we look at the Bureau of Meteorology website, data from sensors such as radars around the country are correlated and predict the data for weeks in advance. But as the information grows, how do we ensure the same quality of service into and out of these massive data stores? The second factor is cloud computing and virtualization, which allows resources to be shared efficiently with rapid deployment and scalability of virtual machines to alleviate peak periods. But with this comes a bottleneck at the entry and exit point of one data center to another. The third is mobile data and its rapid increase as more smartphones, tablets and laptops are introduced. In the case of the Internet of Things, this requires more traffic going through those devices generated by things such as smart cars, wearables and cameras. This leads to a need for routing to be dynamic and load balancing to allow the data to move through the network. As traditional networking is a complicated subject and out of the scope of this project, I'll only briefly describe how it works. Generally, there will be more than one path between a source and destination, and so the routing protocol needs to pick the best path to achieve the highest quality of service. This will be chosen by some type of performance measurement. The simplest way being the shortest path, where the routing table will determine the least amount of hops or nodes to reach the destination. Other parameters can help the decisions, such as the type of transport media, Ethernet or wireless for example, or whether there is a link delay or congestion. If you look at this diagram, this route has less hops than this one and would be the preferred path. Traditional networking has been designed with the idea of all traffic being close to equal. Prioritizing traffic, load balancing, and security routing have all been attempted with cumbersome programming and error-related issues, but does not allow for dynamic changes based on real-time congestion and downtime. If a change needs to be made to the topology of a traditional network, each device connected to that change will require some type of programming. Where in traditional networking, each decision is made within the individual 14 device, SDN decouples these functions. The control plane becomes a centralized brain called an SDN controller, which makes the decisions required to forward the traffic, and the data plane continues to move the data from one switch to the next under the instruction of the SDN controller. The switches can therefore be relatively dumb and require only a very small amount of initial setup programming. The dominant protocol, defined by the Open Networking Foundation, is the OpenFlow protocol. OpenFlow is used between the SDN controller and the data plane. This protocol is open source, which allows anyone to see how it works and encourages people to contribute. Being open source allows all routing and forwarding devices to use the same protocol, freeing enterprise from having to be vendor specific when choosing equipment. So some of the advantages over traditional networking include simplified topology changes. Programming is only required in the SDN controller. Every time a switch receives a packet which they don't know what to do with, they will ask the SDN controller and the controller will simply return an answer. This will be stored in the flow table in case another similar packet is received. This makes SDN more reliable and secure by reducing programming errors. SDN enables traffic to be prioritized easily and can be specific to the session, user, device, or application. For example, you can specify between the hours of 12 and 2 a.m. all traffic to cease except for backup data to the cloud, or that if an intruder alarm activates in the safe, the camera video stream takes priority and alerts the security company with live footage. You may need to route your sensitive data a certain way, and although this can be done with traditional networking, it can be hard to maintain and ensure integrity. Routing based on security is much easier with SDN and more error resistant. SDN really shows its worth when it can dynamically route unpredictable traffic demand. As the load increases, it will simply direct the traffic a different way or ask the virtualization management to provision more networking resources. It can also alert management to help prevent a denial of service attack. Any new ideas can be programmed without waiting for vendor updates. The fault finding and monitoring capabilities of SDN far exceed those of traditional networking. Where at present long system logs are interpreted by a systems administrator, with a centralized management system, all the information is correlated and pinpointed to a single point of failure. This helps to keep excellent quality of service for the user's experience and lowers downtime. The final advantage is that SDN will greatly reduce your capital and operating expenditure. No longer will you need expensive vendor-specific equipment, and your operating expenditure will decrease as the programming reduces to one centralized point. I haven't talked about SDN being faster than traditional networking, as this technically isn't the case, but it does appear to be faster because of its reliability and scalability, which reduces bottleneck issues. But as the processors get faster and the media, such as optical fiber, is installed, networking in general will become faster. Some shortfalls mentioned in my research are A centralized SDN controller can be seen as a single point of failure. As much as I have up until now talked about the SDN controller as if it is one machine, it is possible and highly recommended to deploy more than one controller located in different locations. A second issue is that the open source structure allows network administrators to develop their own applications or APIs to control the switches. This can be an advantage in the fact that you can add only the APIs that suit your needs, but it also requires network administrators to have a fair bit more programming skill than most we currently have. So what effect does software-defined networking have on the Internet of Things? Big data, cloud computing, and mobile traffic all contribute to the unpredictable traffic patterns which are relieved with the deployment of software-defined networking. The fact that a centralized SDN controller is more efficient to program and maintain will solve many error-related issues, leading to the improved quality of service for the user. It addresses the high bandwidth, unpredictable nature of today's networks and dynamically alters traffic flow and automatically provisions additional networking resources based on demand, priority, and security to give the consumer a greater user experience with increased reliability and integrity.